Do you know the difference between print and probe command in VLSI SPICE? Do you know what are the three major areas of VLSI which need SPICE for electrical characterization? Do you know the various kind of trigger and target philosophy that are used along with the measure statement in VLSI SPICE? Stay tuned till the end of the video to know all the answers. Hey guys, welcome back. In today's episode, we are going to discuss the below points. First, we will talk about the print statement and we will give couple of examples so that you can understand how this is used. Next, we will talk about the probe statement and we will also give some example so that you can understand how this is used. And by covering these two sections, you will be able to differentiate how the print and probe command are different in terms of the output. Next, we will talk about the dot measure statement. We will go in detail, and this is the smaller shorthand of dot measure, which is usually written in the SPICE deck to save some characters and for quick and easy writing of the command. Next, we will talk about the significance of dot measure command in VLSI, where in the different areas of the VLSI, this has an impact, where the measure has an impact in the different sectors of VLSI. Next, we will go through the basic example of dot measure command. Next, we will understand the trigger and target philosophy which is used along with the dot measure through infographics and example. Infographics and example will complete your knowledge. Next, we will talk about different flavors of the dot measure when it is used for find and when. That means when something has occurred. Obviously with example. Without example, it's difficult to understand. Finally, we will talk about the dot measure, how the parameter that we have already learned, that parameter thing, how we can club it with the dot measure to calculate complex equations. In a nutshell, in today's episode, we will talk about the print statement, the probe statement, and different flavors and usage of the dot measure statement. So this is the menu for today. Without any further delay, let's begin. Today's episode is focused on the output control of the SPICE. So this is the philosophy that we are going to cover in the entire episode today. So let us start about the print statement and example. So this is a simple print statement. We have a dot print, then we have a type, and then we have voltages. And where does the output goes? When you give, all the output will go to the terminal where you are running the SPICE, as well as they will be captured in the log file, which is nothing but a text form of whatever comes to this particular terminal as a .log file. Obviously the .log file is a text file. So whatever you give as a print command will go to the terminal, you can see there, as well as in case you are running it through the LSF, you can get it after the run has finished from the .log file. Next, here is the print statement and you can see how it is used. The node. So circuit has nodes, right? All like this nodes. So these nodes will have voltages and in between say there is some component, right? So that element will have the current. For I, it will be the element. For V, it will be the node or parameter. Parameter, how it will be there? Equation. And this thing we will cover at the last slide. So you have to wait for that. However, all these things, whatever you give in the print will come into the terminal as well as in the log file. The dot print line defines the contents of a tabular listing of the output variable. Generally, it is comes as the table. When you give all of these things, they will come in a tabular format. The type, here we have talked about the type. The type are like the analysis types like DC, AC, transient, noise, these two, for which the specified output is desired. Generally, when we run a SPICE, right, we do any one of this type of analysis. So we also have to provide that analysis type here. That is mandatory. Now let us see some examples that will clear your mind. Print, this is tran, that means we are doing a transient analysis. Here we have V4 and V in. So we have voltage and current measurement values. So this will go into the terminal as well as in the log file. Next we have print, then we are doing a DC type of analysis, then we say V2, I, V, S, RC, it's a component, and V between the two nodes. So there are two nodes here. Here, this is 23 number node and this is 17 node. So in between, what is the voltage? We are getting that value in the terminal. Again, we have print and then we have AC type of analysis, and here again you can see this is VM. Again, this is between two nodes 4 and 2. VR is at particular node 7 and VP is again between two nodes 8 and 3. Now here we have the print, and now this is a good feature of the print that we can also go down the hierarchy in a sub-circuit. So sub-circuit is defined as x1 dot something will be here. We need all the sub-circuit current, so we have to give a asterisk, right? And also there is another way of giving a question mark. So this way we can get all the sub-circuit currents. Now, suppose there is a farther down deep level of hierarchy. So x1 dot x2. Obviously, the VLSI designs will have different hierarchy. So there is a block, inside that there is a sub block, and again inside that sub block there will be another further sub block. So this way we can go down and then we can get all the currents like this I sub, and I sub is like that x dot a and like that. So this way you can get the different values of current and voltages, right, down the hierarchy, and this way you can get at the top level, that means where you are doing the analysis, right? And this way you can go deep down inside the hierarchy. We are done here with the print statement. Let's move on to the next slide. Probe statement and example. Let us see how the probe statement functions. Here you can see there is dot probe, then we have a vector, then we have further vectors. Probe is similar to what we measure by the multimeter, connecting it continuously with the breadboard and wires. Otherwise, you can imagine that you are connecting a CRO. So probe is that kind of operation. So dot probe, there is another type of way of using it, the analysis type. And then we have the things that we want to print, current, voltage, etc., whatever is there. Use probe significantly decreases the size of simulation output file. When you probe specifically to a set of voltages or currents, right, that will discard unnecessary voltages and currents to be saved in the output database or output raw file. Analysis type is the type of analysis for the plot, like we do the analysis DC, AC, transient, noise, or distortion. So all these types of analysis we do. The analysis type has to be specified along with the probe. You have to remember. Next, OV1, the output variables to be plotted. As I mentioned that these are the output voltages, currents, etc. So these are output variables. These are voltage, current, or element template variables from a DC, AC, transient, noise, and distortion analysis. Names of the vectors to be saved in the raw file or the DB file. Sometimes it is DB. So DB file or the raw file will contain the output variable in terms of the waveforms. Examples, let us see some examples to better understand the probe command. Probe I, V in, then we have input and output. So these are nodes, so we will get the values of these things. This is a simple use. This is another use. Next we have the probe AC, then we have voltage nodes. So this is the most used form, right? We have the analysis type and then we have the nodes or elements. This is a very simple thing to understand and simple command to use. And if you forget to give any probe, right, your output raw file or the output DB file will be empty. That we have already discussed in the troubleshooting episode. So here we are done. Let's move on to the next slide. Dot measure, abbreviated dot MEAS statement. Let us see what's the philosophy and the examples. Dot measure is a post processor. That means once your probe command is done, right, the waveform has come into the DB or the output raw file. The dot measure will operate on it and give you some specific value. The dot measure statement is used to analyze the output data of a transient AC or DC simulation, rather than you can say all these types of analysis. These infographics help you to understand. So once your breadboard is ready, there are multiple things in it. You use the multimeter to get a particular value in between 2 points or 2 nodes or a particular pin, right, with respect to the ground. So this is the purpose of the dot measure. Dot measure is a kind of getting a fine-tuned value of what you are looking for. The dot measure command is executed immediately after the simulation has finished. So it operates once the simulation is finished and the entire waveform is saved in the DB. It prints user-defined electrical specification of a circuit. Generally, this is used for the electrical characterization. What we do with the SPICE mostly used in the VLSI electrical characterization. That's why the dot measure is a very important thing. From one simulator to another simulator, this dot measure can have different names. However, the purpose of the target will be the same. 7 fundamental measurements modes. So there are 7 category of things that we can measure. That means we can electrically characterize with the dot measure or the measure command or the measure philosophy, you can say. What are these? Let us see. First one is the rise fall delay. Next one is average, RMS, mean, max. These things I think you are already well aware from the definitions from your textbook. What is the average value? What is the RMS value? All these things you can measure with the dot measure command. Then we can find with respect to time, find when. So find when this is this value. So you will get the time. Next is the equation evaluation. This is another form of thing that we can do with the parameters and all. We will come to know in the last slide. Next we have the derivative evaluation. That is again comes under the equation and etc. Integral evaluation. And finally, the relative error. So all these things we can measure or we can get the values as a electrical characterization from the measure philosophy or the dot measure command, whichever applicable. Any simulator can have this philosophy with a different name. So you must be well ready to accept the philosophy and not just stick to the name. So here we are done talking about the measure philosophy, how it performs, on what it performs. We are done here. Let's move on to the next slide. Dot measure in VLSI. Now, this is a kind of philosophical slide rather than having explicit details to know where the dot measure used in VLSI. For all IP related electrical characterization, that means if it is a analog IP, it is a analog digital mixed mode IC, it is a high speed IP like USB, SerDes, all these things. So there the electrical characterization is done by SPICE or SPICE Verilog co-simulation, and there the dot measure philosophy or the measure philosophy is used for this type of characterization. And next is the dot leap liberty characterization. You already know this is a standard cell characterization. Obviously there will be an engine which does the characterization, but at the unit, that is the cell level or the leaf level, when a electrical value is characterized, that is with the help of the measure philosophy. And sorry about the typo here in between the two characterization words. Okay. Next point is the SPICE dot measure. SPICE is broadly used in analog design and analog electrical characterization. So there you will see the dot measure philosophy. So that means in the 3 broad areas, this is the analog design, this is the IP design, and this is the standard cell design. So all these areas, you will find the impact of the measure philosophy to measure electrically characterized values. In upcoming slides, you will know the philosophy in minute detail, what are measured, how they are measured, and you will see the graphical example. So done here. Let's move on to the next slide. Dot measure basic example. So here you will see some basic examples, fundamental examples that will help you to grasp the meaning. So this is the syntax. We are not going in detail. Here is the basic set of waveforms that we generally find. So this is sine wave, this is square wave, this is triangular wave, this is sawtooth wave. You know all of these waves. And let us see some example. First, dot measure run. So you can see in this x-axis we have time, that is t. And here we have some voltage or current value. So this is a transient analysis. So tran, then average value, average of V10 from 10 nanosecond to 55 nanoseconds. So suppose this is V10 and we are trying to get the average value here by the AVG, average mathematical performance. Average, you can see average, mean, max, etc. will be there. And from 10 nanoseconds to 55 nanoseconds. So this is 10 nanosecond and this is 55 nanosecond. So within that we will calculate the average value. So the mathematical form of average calculation will be applied on this particular waveform for this time window. Now we can replicate this if we change V10 to other waveforms. So we can calculate the value for within this particular window for all of them. For that we have to write multiple measure statements. We will change here V10 with, say this is V10, V11, V12, V13 like that. Next is the max value, that is max V12. Say this is V12, 1 and 2, in between 1 and 2 node number 1 and 2, from 15 nanosecond to 100 nanosecond. So this is 15 nanosecond and this is say 100 nanosecond. So we will get the maximum value. Generally this is a flat, right? But however, there can be a maximum value somewhere here. We have to detect that. And if we apply rather than a square wave, if we look at a sawtooth wave, right? This is much more applicable because here we are getting a maximum value. Here is the maximum value. So if we try to superimpose this kind of measurements on a sawtooth wave, right, what we will find that within this time window, these are the 3 peaks, 1, 2 and 3, and we will get the maximum value. Say this is the maximum peak. So we will get the maximum value using this particular dot measure command. Next, we have the dot measure TRAN. So you can see I am writing in both ways. The dot MEAS is the shorthand and the full form the dot measure. TRAN, then Y max, then max value from 2 milliseconds, 3 milliseconds. So again, say this is the waveform, the 2 milliseconds to 3 milliseconds. We want to find the maximum value of V2. So this is V2. This will operate on this waveform and we will get the maximum value. Then again we have the dot measure TRAN, Y max, max at V2 from 2 milliseconds to 3 milliseconds. So this will give the max at V2. Obviously this will not give the Y value, rather than say if this is the max at this value, right, from within this window, it will give the time value. Here the time axis, it will give the time T of Y max. You can read this as T of Y max. So this will give the time. So the max value within this particular window, right, 2 millisecond to 3 millisecond, we get here, right? This is the max value which we get from here, right? But we want to get the time here. At what time? So this will give the time. Next, we have TRAN, YPP, then PP, and this is peak to peak, right, from this. So peak to peak values we can get like this. So peak to peak value means, say we have a square waveform, right? Peak to peak means this peak to this peak, peak to peak value. These values we can measure in this way. In case of a triangular wave, peak to peak means from here to here. So this way we can get a peak to peak value. These are philosophy, all you have learned in your undergraduate level textbook. Next, we have the RMS value, YRMS. So RMS values you will get of say any voltage V1 from 2 to 4 milliseconds. So this is 2 millisecond and this is 4 millisecond at time. So this is time axis, right? And there you want to get the RMS. So you can get all these RMS values 1, 2, 3, 4 by this here. Here say this is V1. And if you change V1 to 2, 3, this is V2, this is V3, this is V4. And this way if you change, right, you will get all the RMS values of all these kind of waveforms. So by this. Next, we have the TRAN, then average value, Y average value. And here we give the average, and again we have from 2 milliseconds to 4 milliseconds. So this way again you can get the average value. Say we are taking this time window here, and if you change V1 to other, so this is V1, V2, V3, V4, you will get all the average value of all these separate waveforms. This way you can get the basic measurement values. Now we are done here with this simple set of measurements that you can do with the measure. Let us move on to the next slide. This is an infographic slide. Here we will understand the trigger and target philosophy using multiple waveforms. For your knowledge, let me mark here. The trigger is marked in green and the target is marked in pink in all of the waveforms. Second waveform, third waveform, fourth and fifth waveform. All the waveform we have kept the same convention that we have marked trigger as green and target as pink. Now, this is a waveform where the wave is rising. So we are calculating rise time. So trigger means the measure will trigger here and the target means the measure will finish here. So this will measure the rise time. Philosophically, first you have to understand, then only you can use the dot measure command accordingly, as you are going to see the examples in the upcoming slides. Now, what the fall time, right? The wave is falling down here, right? You can see. So the trigger will start here and the target means the measure will finish here. So in between, it will find the fall time. Obviously, it will be measured in the time axis. Here is also we will measure it in the time axis. But however, the trigger and target will be on the actual waveform. And in case, see, you are doing this trigger and target, right? And the waveform is flat. What will happen? the measurement value will be corrupted. You have to keep that in mind. We have talked about this in the SPICE troubleshooting episode. Now, there are two waveforms. One is the clock, which is coming from the clock. Another is Q, that is the Q of your flip-flop. The trigger can be at the clock waveform and the target, that means when the measure will finish on the another waveform, that is Q. And generally, this measures the clock to Q delay. This is a very widely used measure, clock to Q delay. Here, the time will be measured in the x-axis, starting the trigger at this clock and finishing the measure at this target, and here this clock to Q delay will be measured in the time axis. But here you notice one thing, the trigger lies on a different waveform and the target lies on a different physical waveform. So this is the philosophy of trigger and target. So they can be on the same waveform, they can be on the different waveform. Now here the trigger and target, here you can understand, right? These are on the same waveform. What we are trying to measure here is the on time. That means how much time the waveform is on the on state. So this is typically at the 50% and this is typically at the 50%. Trigger, that means the measure will start here at this point, and the target, that means the measure will finish at this time, and this from the x-axis the time will be calculated. This much time is the on time. Again, to remember, both trigger and target will be according to the waveform. Next, we calculate the time period. From the definition, we know that once a complete cycle is here. So you can see the complete cycle is here in VLSI. Whatever we measure for the time period typically at the 50% of the voltage. Our trigger will start here and the measurement will finish here, and this way once we drop this on the x-axis, the time period, right, this particular time value will be counted as the time period. Through multiple examples, you can understand the trigger and target philosophy lying on different waveforms, maybe lying on the same waveform, but however the waveform should be present there philosophically in proper shape and size to get the values. In case you are getting a wrong value, open the waveform, check whether there is something wrong with the waveform. So that's the philosophy and infographics for trigger and target. Next, we are going to go to the detailed example of this trigger and target. So done here, let's move on to the next slide. So here, let us see some trigger and target examples. Dot measure command measures the different DC voltage, frequency or time between 2 points selected from one or two output vectors. There will be an output vector or output waveform. There we will measure, as we have seen by the infographics in the last slide. Measurements of TRAN analysis start after a delay time TD. Generally, we add a delay time because there will be a startup time of the circuit. Generally, that startup time of the circuit or the turn on time of the circuit we put as T delay. So T delay you can find in the command, and philosophically this is the wake up time of the circuit. So we give that time of delay T delay to get the circuit get on. And after that on time, that means when the circuit is waked up, it performs as per expected. And that's why we keep a provision of TD, that is the T delay, that is the initial delay in the dot measure command. Here is the syntax, we will not go in detail, and the current examples are using the transient solution. So let us have the waveforms again. It will be better to understand through the waveforms. First, you can see that is the trigger and target are present, and you can see both are on V1, right? So that means single waveform. So you can see V1 is here and V1 is here. We are operating on the same waveform, and you can see from rise 1 to rise 2. So this is rise 1 and this is rise 2. Value is 0.5. So this is 1 volt, right? At 0.5 volt, we get the T difference. So T difference will be here in the time axis. Again, this can be for this waveform also, but it is not very much interpretable. That's why I am not giving here. Rather than for a square wave or a pulse wave, this is much more applicable, because in digital electronics or the analog mixed signal electronics, right, this will be more applicable, the square wave or the pulse wave. Now again, you can see here, this is V1, this is V1. So this is rise 1 and this is rise 3. So this is rise 1, then this is rise 2, and this is rise 3. So you have to identify in the physical waveform, right, what you are trying to measure. So this is again value 0.5, value 0.5. So whatever time value is within this time window, this will be measured. You understood the trigger and target philosophy from the infographic slide, and here you can easily apply. Next example, Here you can see the trigger happens at V1 and the target happens at the V1. So these are same. We have rise here and fall here. Earlier both were rise, but here is the difference. This is rise, this is fall. So this is the first rise and this is the first fall. So in between we are measuring the time. So this time we are measuring in the time axis here in this third example. Next we have again the trigger at V1 and the target at V2. So these are two voltages and here we call it on the fall 3. Say this is V1 and this is V2, right? What will happen that it will be the fall 3. So this is let me erase it and draw it again. So this is fall 3 and accordingly this will be fall 3, right? We expect some time difference. So let me check, this is fall 3 rather than the previous one, right? So what will happen that some value marker will drop here and some value marker will drop here and we will measure this time. Although here value I think has 0 has come, it will be some numerical value. It is a typo here, please ignore this. And here you can see trigger and target on the two different waveforms. Now here trigger is on V1, target is on V2 and you can see the value is minus 0.6 and minus 0.8 and cross 1. So this is cross means whenever they cross 1. So that means this will be like this. So at minus this value minus 0.6 and similar waveform, say this is these two waveforms we are talking about. This is 0.8. So these two waveform will be considered and for that first one this is 0.6 and cross at 1. So 0.6 is here, right? Minus 0.6 cross 1. So one marker is dropped here in the time axis and for target this one, say 0.8 is here, right? Somewhere here and this is dropped here and in between there will be a time difference. So that time difference is measured. Cross means once these values are just crossed, that means these values will be explicit. So let me erase it and you will understand better. So this is something 0.8. So this value, whenever this waveform is crossing, just drop a marker at the x-axis. That means the time axis. And here, when it is crossing the 0.6, here just drop it. This is the difference that we want to measure. So here are two different, so V1 and V2. So this is V1, this is V2, and this is where we are measuring the time difference. So there will be multiple things that you can measure using this measure philosophy in the different type of VLSI characterization that we have already spoken in few slides back, where we have shown 3 different areas where these are applicable. The last example, trigger at 1 millisecond, target V2. Value is 0, cross 3. Say at 1 millisecond, here we are fixing and target is V2. Say this is the V2 waveform. Value is 0.8, cross 3. Third time when it is crossing. So that value will be given. This is the final. That means this is a target and say trigger is done at the 1 millisecond here. So this difference will be given by this. Trigger at 1 millisecond. So this is the trigger happening and target is V2 and value is this when this crosses. So this cross will be done here and we drop a time marker here and this value, this particular time window we are measuring by this one. So this is the philosophy. We are done with lot of example, infographics and all these things combined. Now let us move on to the next slide. Dot measure with find and when. Now we are seeking the time when things are happening, right? Until the last slide, mostly we were talking about how much time it is taking, and now we will be focused on when it is happening. That means find when this is happening. So that means we have some voltage thing happening at some point, and we will drop a marker in the x-axis, and we will find when this is happening. The find and when functions allow measuring any dependent or independent time, frequency or DC parameter when two signals cross each other or a signal crosses a given value. That means we have two signals which are crossing each other at some point, or one signal that is crossing some particular value. So this is x-axis and this value we are crossing. In this case, we use a find and when. Find and when can be used together or separately as the below combinations. So this is what we give as our looking glass to find when it is happening. This is the syntax here, right? Again, we have a large syntax here. We have further large syntax here. And we have another syntax here. But don't worry, we will not go deep in the syntax. The syntax is there. We will understand it through example. So let us move on to the next slide. So here we will understand the find and when through examples. That is better way to understand. Here again we will need the waveform, so we keep them. Example, start here. Dot measure tran fifth when this voltage value is equal to 2.5 at rise 5. So this is V oscillating output, right? And it is 2.5, right, at the rise 5. So 1, 2, 3, 4, 5. So it will go beyond our waveform, right? So we consider this is rise 5. So this is rise 5, right? So it will be 2.5. So 2.5 means this. And when means at what time point? So we are getting the absolute x-axis time point. That is t equal to t1 when we have this rise 5. Dot measure time of the fifth rise of the node oscillating out at 2.5 volt report as the fifth listing. So that is the fifth rise time. First rise, second rise, third rise. First rise, second rise, third rise. So this way the rise and falls are measured. This is the first fall, second fall, third fall. First fall, second fall, third fall. So this way first, second, third are measured. Next, we have the dot measure tran, then find, then we have V out. This is another waveform when V in is equal to 40. So this is V out and this is V in. Here we want to find V out, that means here when V in is equal to 40. The measure V out when the V in is equal to 40 m towards the variable result. So this is 40, right? What will be the value of V m? This value will be stored. This is time wise and this is value wise. That means at 40 m, so this is at 40 m, this is x axis, 40 m is here x axis, and at y axis whatever we are getting in the V out, this is a V out, this is V out and this is V in. So V in we are taking the x axis, the value, and we are getting the y value at another waveform. Next, measure tran t value when V2 equal to V1. Say if these two waveforms are bit shifted, right, then if this peak is just below this, right, there will be a value of time, right, when this will be done. Then, and it could be that rise equal to last. So last rise is this one. So here, suppose we drop a marker and at this value and this value are same. We want to know this time value here. This time value goes here. Measure tran y eval, find V2 at the last fall. So this is V2, this is the last fall when V1 is equal to 0.4. So this is V1 and also here this is 0.4 and it is minus, and we drop a marker here and we find the value here. That means we get the y value. Earlier we are getting the t value. T value means x value. Y value means we are getting the voltage value. Next, again we get a similar y values. Find V2 when V1 equal to V3 at fall 2. At fall 2, this is the second fall when V1 equal to V2 at some voltage V1 equal to V2 at that particular time. V1 equal to V3. This is V3. So V1 equal to V3. These two values are same at fall 2. Find V2. This value will be find out. This is V1, this is V3 and this is V. That's all. Next we have y value, find V2 at 2 milliseconds. So this is a very simple thing. This is V2, find V2 at 2 milliseconds. So this is 2 milliseconds, say this is 2 milliseconds, go and find the y value. This is the y value. So this is the find and when philosophy. Find can be used independently, when can be used independently. So this is a independent use of when, this is the independent use of find, and this is the dependent use of find when. So all are shown to you. Here we are done with the waveform, philosophy, everything. Now let us move on to the next slide. Now here we have the dot measure with the PARAM equation. Use this statement to evaluate an equation that can be function of results of previous dot measure statements. Sometimes we have to calculate some value on the go using dot measure. And there we have to use the parameter that we have already learned in the SPICE in previous episodes. And we have to form an equation. And from that equation, we evaluate some value on the go. The equation must not be a function of node voltages or branch current. So this must be remembered. Dot measure, then measure type, then parameter name, then measure equation. This is the generic form. And this is the syntax. And this is another syntax. So here are multiple set of syntax could be there. This is with find and this is just a simple thing. This is find at Now let us see some example. You understand anything with example, so I'll focus on the example rather than in the syntax. So here dot measure is a transient type. We find t meet and we have parameter. Here we have t from t2. So we have 2 time point. We have this and we divide by 2. We have t from and t2 and we have these 2 value, and mathematically we are getting the by 2 value t1 plus t2 by 2. So this is done by the parameter. Yes, with some previous measure command we have measured this t1 and t2 separately, and then we calculate t1 plus t2 by. Next we have the parameter, then f val equal to 5. It's a simple thing and this will be used in further calculation. Then we have the dot measure tran y at parameter f val, right? This is constant plus 7. So this way we can use a parameter inside a measure. Then we have parameter p out, then diff is 50 micro. Now we are going to use this. Let us see how. We have dot measure tran p diff trigger at 1 millisecond, target at v2. We have already come across this type of trigger target already, value at cross 3. So what we get from this one, t diff, and here we have v out diff. Now let us check. With this measure tran command, we give a check, right? Then we give param. We have a ternary expression here. This is a ternary operator, right? We know all this from our long back C language. So from there we decide a value to this by comparing this value and this value. That means this is what we have hard coded, and whatever we are getting t diff from this measure, we are comparing them with a ternary operator, and finally we are storing the result here. So this is a part of characterization things that you have to do in VLSI, and that's why I am going through thorough exam. Next we have measure, and then we have tran, that is a transient, and v test find is a find one. Then we have this value at this one. So this value will be find. Some waveform is there and find at 2.3 millisecond. Okay, this is x value. This value will be find. We are done here with thorough example how the parameter can be used inside and along with side by side the measure commands along with all other TRIG-TARG things. So there could be a complex mix and match of all the measure commands that I have shown you in this entire video through thorough example. They can be used in the electrical characterization done in VLSI in any of the sectors of whether it is could be a IP characterization, it could be a mixed signal characterization, it could be standard cell characterization, anything or any other type of electrical characterization that you can find in any kind of new design. So that is we have learned in today's episode. We're done here. Let's move on to the next slide. Thank you very much for watching up to this point, and don't forget to like, share and subscribe. In case you have some dislikes, put that as in words in the comment section down below, and bye for today.